So thank you so much for joining me today. My name is Isaac Sorensen. I'm going to be taking you through this effective waterproofing presentation today. Wanted to thank you for your time and look forward to getting into it. Just a few housekeeping things before we get going. If you would, during the presentation, if you have questions, just put them into the Q&A box and direct them to all panelists. We will attempt to answer them as the presentation is rolling. In the event that we are not able to answer it during the presentation, we will be getting back to you via email with your registered information to make sure that all questions are answered. There will be a YouTube recording of this available on our YouTube channel. And if there's any interest in receiving the presentation, you can email us info@wrmeadows.com. All of those that signed up with an AIA number will have these credits submitted to the AIA for your continuing education, and the certificates will be provided to everybody who provided information to us. So with that, I'm going to get going. This is a basic presentation. It's not a deep dive into effective waterproofing. You can look out for our technical presentation this late fall on detailing waterproofing. This is more of an overarching understanding of encompassing a effective waterproofing installation. So a little bit about W.R. Meadows. We're a family-owned and operated company to this day. Growth and innovative focused company, founded in 1926 in Elgin, Illinois, just outside of Chicago. Regional manufacturing throughout North America with 13 facilities, 3 in Canada, the rest here in the United States. 1926, as I mentioned, in 2021, we opened a very exciting part of our business, our Innovation Center in Hampshire, Illinois, and we look forward to updating you on some of the progress and exciting things that are coming out of W.R. Meadows currently. Some of the affiliations across the country. Just wanted to make mention of these wonderful organizations that we involve ourselves with, and look forward to meeting you at many of the industry organizations around the country that we do participate in. Also, continuing education opportunities there as well. Some of the Meadows products, product portfolio, building envelope. Obviously, that's part of what we're going to be discussing today: vapor barriers, air and water, and vapor barriers and waterproofing. We have a sister company, Blue Ridge Fiberboard, soundproofing, structural decking for roofing, and insulation board. Concrete restoration, construction liquids, Division 3, large Division 3 portfolio. Decorative concrete, expansion joint materials. That's some of where we started with expansion joint. And to this day, I believe we're the only American company making expansion joint in the United States. Joint sealants, and just a single source here. A quick look for those in waterproofing. We have solutions for all of your waterproofing needs: vertical surfaces, planters, drainage, protection course, blind side, underslab, horizontal split slab, and negative side as well, of course. So we're going to get into the presentation. This is an AIA accredited presentation. At this point, I'm going to be going into the AIA rules of non-proprietary discussion about the subject matter, and let's get into effective waterproofing. So the objectives are to discuss the mechanics of moisture movement, resulting issues, explain some of the issues relating to concrete deterioration. We're not going to spend a ton of time on that because discussing concrete can get a little obtuse, but we want to touch on that as that's our most prevalent substrate when we're approaching an effective waterproofing installation. We're going to differentiate between damp proofing, waterproofing, and vapor proofing, and differentiate between negative side, blind side, positive side waterproofing, and identify some of the various systems that are out there in the field as well. So let's get going here. So in the beginning, to identify how to effectively waterproof our buildings, it's important to take things back a step to our knowledge of earth science, maybe 9th grade for most of us, to remember the never-ending cycle of evaporation to precipitation, the ways in which water in liquid and vapor form to create the never-ending cycle of the movement. There are many parts and pieces to the hydrologic cycle, and our built environment, as we place our buildings around the earth, of course, interrupt this cycle in one way or another. So we have to plan and accommodate as best we can to differentiate, to make the different parts and pieces laid out here in the listed bullet points on the left side work. So each of these things we'll discuss in more detail one by one, but it's important to start our discussion on effective waterproofing by remembering that each part and piece of the hydrologic cycle plays an important role in the relationship to our building in the built environment. How does moisture enter the structure? Of course, the presence of water in its liquid form around the structure can be from numerous sources, and in order to select a system that can control water penetration, it's important to consider all of these sources. These include the water table. The depth of this needs to be determined and understood. Site drainage, of course. There's naturally occurring site drainage, or do alternate drainage methods need to be addressed? Something to consider is that fine-grained soils can draw water from considerable distances. That speaks to the capillarity aspect of the hydrologic cycle. We'll talk a little bit more about that as we keep going here, but that's important to understand that fine-grained soil can draw water from considerable distances, and both of these can be determined by a soil report. Another factor to consider is an irrigation system. So when designing a structure that incorporates this, it's important that the waterproofing and drainage system can accommodate the extra water that's going to be present, of course, as a result. And then there's cracks in the concrete. Of course, concrete always cracks. They're a prominent part of concrete. It will crack. The location of these cracks can somewhat be controlled by the design of the concrete. However, there is also the possibility for cracking to occur that has not been accounted for. Water can enter through these cracks, and so it's important for the system to be designed to accommodate cracking. No matter how good everything is, waterproofing details, we'll talk about this, continuity becomes really the most important factor in creating an effective waterproofing system. Hydrostatic pressure. When considering a waterproofing system to control liquid penetration, it's important to look at two factors that were in that hydrologic cycle bullet points, but they allow for the movement of water. These are hydrostatic pressure and capillarity. So hydrostatic pressure is the pressure, of course, from the weight of the liquid, and its value is directly proportional to the height of the liquid and the density of the liquid. In other words, the deeper you go, the more pressure will be present. So our below grade foundation area, or below grade area, as water builds up on the outside, that pressure is the hydrostatic pressure that we're speaking of. In scientific terms, hydrostatic pressure increases in proportion to the depth measured from the surface because of the increasing weight of the fluid exerting down from the force above. And in international systems, you may see the term pascals used as well. And that's essentially a hydrostatic pressure term. It's a different calculation, but for illustration purposes, 1 inch of water exerting hydrostatic pressure down to the base of a straw would be about 250 pascals. So you do the math, but just wanted to make you aware of that as well. Capillarity is the force that results from greater adhesion of a liquid, we're talking about water, to a solid surface than internal cohesion of the liquid itself, and it's therefore able to literally rise along vertical surfaces. So that means that the liquid rises against gravity. It is one of many scientific anomalies that's attached to the compound of water, which is a really fascinating structure to study. But water, when confined in between single-ply materials or in tight spaces, will literally rise against gravity. So in areas below grade, again, we mentioned that the soil report, even if we're well above the water table, if we don't create capillary breaks in sandy soil, we can see that soil will suck up the water and actually bring it into our below grade area. So being aware of capillarity when we stack single ply materials up against one another and we have a void, the possibility exists for that water to move against gravity into areas that we don't want it to be. So how does moisture enter the structure? Again, we're talking about water and water vapor. Dependent on the difference in temperature and relative humidity, below grade, the diffusion of water vapor is from the ground into the structure. Ambient conditions in the ground are approximately 55 degrees at all time, 100% RH. That's often overlooked. Again, below grade, the RH, 100% at all times. So vapor moves independent of air pressure based on the difference in vapor pressure. We'll look at this just once again in another slide. But as you can see on the right with the vertical wall footing and slab on footing, often will encompass a effective waterproofing in a below grade structure by putting a vapor barrier under the slab, skipping the footing, and then putting a blindside membrane on one side of the vertical wall, or a post-applied piece of waterproofing. Continuity, again, is very important in terms of vapor drive, and then also in terms of water vapor intrusion or water intrusion into the structure. So designing effective continuity keeps water vapor and water out. And as a takeaway from the definition, vapor diffusion can be defined as the transmission of water vapor independent of air pressure as a result of the difference in vapor pressure. That basically just say that from one environment to the next, from below grade in the soil to our interior, the vapor pressure is going to determine which way the vapor is moving. 100% RH at all times below grade. So we have to protect both the substrate and the interior of the structure and account for vapor movement. We're going to go into a description of concrete quickly. As I mentioned earlier in this presentation, we wanted to take a second to just acknowledge that this is probably the most used substrate in a waterproofing structure. And so understanding a little bit of concrete is important. So what is concrete? First and foremost, before even talking about waterproofing, it's important to understand what concrete is. It's the most widely used man-made product in the world. In its basic form, it consists of cement, which is naturally occurring, aggregates, and water. We mix the two. We have a chemical reaction, the hydration, compounds break down and form new ones. The heat of that hydration is realized in the concrete, and then the concrete is formed. Modern concrete essentially was invented in 1756 when a British engineer, John Smeaton, pioneered the use of cement powder, Portland cement, in concrete. The composition of concrete is traditionally relatively simple. However, today's concrete is often a complicated mix consisting of a number of chemical reactions, ensuring durability and longevity. So the advantages: low cost, high stiffness, high compressive strength, not flammable, ease of fabrication. Disadvantages, I think we all kind of are aware of the disadvantages, that it breaks down, low tensile strength, it's brittle. To some extent, the long-term durability is questionable, but when we protect it and when we effectively waterproof, we can protect our concrete for a great installation. Little bit about the chemistry of concrete. Again, we're not going to go too deeply into it, but I want to make you aware of some of the building blocks. Concrete hardens, of course, by hydration, which we mentioned. Cement and water form a paste that coats the aggregate. The paste hardens and gains strength during this reaction. There are a number of compounds formed, the first being calcium silicate hydrate, or CSH, calcium hydroxide, CH, being two of them. CSH is the most important of these because it contributes to setting, hardening, strength development, and volume stability. And CH contributes to providing an alkaline environment, which is beneficial to reinforcing steel, as it helps to reduce the potential for corrosion. And additionally, other compounds such as calcium aluminum hydrate, calcium ferrite, are also formed by the hydration. Those help keep the pH at the correct place to protect the structural steel. So when it comes to determining the strength of concrete, the key factor, of course, is water to cement ratio. And a lower water to cement ratio will yield a concrete which is stronger, while a higher water cement ratio yields a concrete which is less strong. Water also affects the workability and consistency of the mix. And again, that building block CSH I wanted to mention because many of the densifiers, hardeners, surface applied Division 3 construction liquids will affect that CSH. And it's important to understand that that is the building block of our concrete. So limitations of concrete, again, I'm not going to spend too much time here, but I wanted to just point out that one of the most critical forms of concrete deterioration is the corrosion of reinforcing steel, and this is caused by a breakdown of the passive layer provided by the concrete around the steel. So when we have water moving through there, it carries all kinds of negative things, negative ions, chemicals, and essentially carbonation happens where the steel expands, it's carbonated, and the structural steel is compromised, and then the structural integrity essentially of the whole installation is then questionable. So by addressing the exterior, by curing properly, and then by protecting the concrete as a substrate, we can create better and more effectively waterproofed situations, as well as protecting the structure itself. So effective waterproofing, even good concrete can be described as permeable and porous. These are characteristics that are innate in the substrate. Let's talk a little bit about them. So permeability can be defined as the measure of ease with which fluids will flow through a material. Cracks in concrete interconnect flow paths and increase concrete permeability. The progression of these cracks allows more water or aggressive chemical ions to penetrate the concrete, facilitating deterioration. So the lesser the permeability, the more durable the concrete. Again, with different construction liquids, we can address the permeability of the concrete and essentially protect that outer layer and make sure that we're effectively waterproofing, which will also, in turn, protect the concrete. Porosity, the second factor that determines the extent of water penetration is porosity. This is defined as the ratio of volume of openings or voids to the total volume of the material. So in other words, the spaces in the concrete. The most important factor in determining the porosity of the concrete is the water to cement ratio. Again, if we add too much water to the mix, we are compromising the strength of the concrete itself, but we're also creating more pores, essentially. So again, different types of construction liquids will address porosity and are more suited one to the other. For instance, silane tends to work with very low porous materials well. It'll infiltrate that surface layer with very, very small voids or very small pores. Other mixes of construction liquids will address larger porous surfaces such as CMU block or red brick. Siloxane, for instance, is a great covalent bonder on large porous surfaces. So let's get into some of the reason that we want to effectively waterproof. Of course, moisture control being number one. This all to illustrate that except for the structural errors, about 90% of all building construction problems are associated with water in some way. The AIA will back me up and will also tell you that the number one reason for litigation within the built environment is moisture issues. And so this all to say that effectively waterproofing is very important. Between 94 and 1998, the EPA Building Assessment Survey, or BASE, an evaluation, studied collected information about the indoor air quality of 100 randomly selected public and private office buildings in 10 hygrothermal regions. And BASE found that 85% of the buildings had been damaged by water at some time. 45% had active leaks at the time the data was collected. Again, this all illustrating some of the reasons that we saw a lot more interest in studying moisture movement through the building envelope and the enclosure. The drive towards better air barrier systems was built on some of this early data and has driven the code to this point. So obviously moisture control is essential for the function of a building, for occupant health and safety, efficient operation of the mechanical system, and to protect the building from damage. All of these we know inherently, but mold, water introduced into the built environment is detrimental to a functional building. Essential elements of an effective waterproofing and moisture protection system. The essential performance characteristics of an effective system consist of continuity, which I can't stress enough. If there's anything that you can take away from this presentation, it's that continuity will make or break an effective waterproofing system. Durability and structural integrity. To understand the importance of continuity, I like to use the balloon analogy. If you take a balloon and you introduce it to a pin, there's no more balloon. It's essentially void. The same is true for a below-grade waterproofing system. The main layer or portion of that waterproofing system relies on the details, effectively creating a continuous, durable, and resilient system. And without proper detailing and thought of proper detailing, we lose the opportunity to effectively waterproof and effectively protect our buildings. Resilience is defined as a sustainable measure that can be incorporated into the building fabric, so fixtures and fittings to reduce the impact of floodwater on the property, sumps, that sort of thing, the planning of which is, very important. Structural integrity kind of goes without explaining. And then as resilience, as I mentioned, I also wanted to make the point that durability could also mean the reliability of the ancillary parts and pieces to the main waterproofing system. So when we're looking at penetrations and protrusions to our below-grade waterproofing system, picking the ancillary parts such as the types of seals, making sure that pipes are grouted properly, that backer rod, sealant, link seals, all of these different parts and pieces are up to the task of whatever they're going to be put up to in that below-grade application for waterproofing. So the durability of a building also relies on the ancillary parts and pieces of the main membrane, for lack of a better way of putting it. Factors influencing the effectiveness of a waterproofing system. Key factors affecting the efficacy of a system include design, materials, workmanship, and quality assurance. Although good design and quality materials are essential, poor installation and substandard workmanship, along with a lack of job site inspections, can completely destroy the efficacy of a system. So as it relates to design, obviously mock-ups are helpful, creating job site meetings, anything that we can create to create effective communication on the job site, the different trades that will be working on top of an installation, sequencing discussions, all of that become very important in the effective waterproofing of a structure. Materials, of course, we'll talk a little bit more about that. Workmanship, hard to control, but again, with proper specification in place of mock-ups, job site meetings, and sequencing discussions, we can create that opportunity. And of course, quality assurance speaks back to the specifications as well. So a proper below-grade system of waterproofing proper below-grade system would incorporate waterproofing, vaporproofing, and drainage. And let's get into some of these. So there really isn't one waterproofing system for every situation. It's important to differentiate between those different parts and pieces that I just mentioned and get into the definitions specifically. So waterproofing is defined as a material that's able to resist the passage of water under hydrostatic head pressure. And the key is hydrostatic head pressure. A waterproofing material is not inherently vaporproof, and a waterproofing material will be able to withstand hydrostatic head pressure, very simply put. Damp proofing is defined as the resistance of water in the absence of hydrostatic head pressure. So often we will see damp proofing specified into areas where there will be hydrostatic head pressure, and that is an incorrect use of damp proofing. Damp proofing materials typically don't bridge cracks either in concrete that may occur over the course of a building's life. And I can't even tell you how many calls I get yearly from residential homeowners looking to incorporate a proper waterproofing system after having uncovered the fact that their below grade structure was, quote, waterproofed with a damp proofing material that then cracked. So just be aware of that. That damp proofing really isn't supposed to be in place where hydrostatic head pressure will be realized. Vaporproofing material is one that is totally immune to the passage of gas under pressure, and in this case we're talking about water vapor, or vapor from water in the form of a gas. And vapor diffusion occurs due to the difference, again, in vapor pressure. And below grade, this is the method of moisture movement that needs to be considered. Above grade, there's moisture movement by air pressure differentials, but this is negligible when below grade. It is important to understand this vapor movement when it comes to the selection of waterproofing materials or various floor coatings and their vapor permeants. If materials are used that are not breathable, such as a number of urethanes and epoxies, and they're subject to vapor diffusion, premature failure of the coatings can occur as a result. So again, below grade, there may be an interest in allowing that vapor to move through. In some instances, we need vapor proofing. And certainly in a below grade effective waterproofing situation, we should consider water vapor movement. Positive side waterproofing. Now we get into kind of the meat and potatoes of the presentation, where we discuss some of the systems, the ways that we incorporate effective waterproofing, and then some of the systems that are available. Positive side waterproofing is a system that's applied to the exterior or the wet side of the concrete. This is currently the most predominant type of waterproofing and includes all types of commercially available systems. So Blindside, which we'll discuss a little further, is a positive side system done backwards or inside out. Self-adhesive, fluid applied, and cementitious are other forms of positive side waterproofing. This type of waterproofing protects the interior of the facility from moisture infiltration and protects the structural components. As we mentioned earlier, that's why we discussed the concrete. It's important to protect it, the concrete and the steel. The primary advantage of positive side waterproofing is that it prevents water from entering the substrate itself. Again, if it's not continuous or has full continuity on the positive side, there are areas of that substrate that are going to be available for moisture attack, essentially, over the course of that concrete's life. So if we're protecting the substrate, this can help provide freeze-thaw protection in those climates where this occurs, as well as provide protection of the substrate from any potential corrosive components that may be in the groundwater or moving through the substrate within the water. One major disadvantage of positive side waterproofing is that after installation, the system's virtually inaccessible for repairs. So the result of this is that any issues with the waterproofing system will be very costly to address. And as mentioned, most of the waterproofing systems can be applied on the positive side and include sheet membranes, fluid applied membranes, cementitious waterproofing, and flexible cementitious coatings. Most of the systems also require the use of a protection board to protect it from backfill. We'll talk a little bit more about those towards the end of the presentation. And it's important to check with the manufacturer to determine what kind of protection needs to take place. Alternatively, composite drainage boards can act as protection layers in some instances, but will also provide great drainage around the structure, sometimes negating the use of drainage fill material or protection course. So let's talk about negative side waterproofing. Negative side is applied to the interior side or the dry side of concrete. These systems include cementitious coatings and crystalline materials. The key criteria for these types is that they are able to withstand hydrostatic pressure that will be acting on the bond of the material. Now you can notice on the left, the water pressure coming up against the substrate. On the outside, we have that concrete vertical wall, and then the coating creating the negative side waterproofing system. That bond is integral to the performance of the system. So in order to make sure that the bond isn't affected horribly, sometimes the breathability of materials is important to prevent water vapor issues and debonding of the waterproofing system from the substrate, which can occur with non-breathable type systems such as epoxies and urethanes. Sometimes you'll go into a basement and see little pockets of water or bubbles behind an epoxy or urethane system. That's where the water drove its way through the substrate, hit the dew point there at the bond, and turned into liquid water, and then it's just literally held in the substrate and up against the material, which can then debond over time and create issues. Negative side waterproofing allows the water into the substrate, as I just mentioned, and may be an advantage for curing, but also a disadvantage, far more disadvantages, as there's potential issues such as corrosion, deterioration from freeze-thaw, all of those negative things when we get water into the concrete substrate. So in addressing materials, we're going to get into some of the materials that are available on the market for effective waterproofing. We want to think about these things when we start our material selection for an effective waterproofing system. Obviously, the working life of a product, does it have legacy? Has it been out on the market? How long has it been out on the market? Is there precedent set with jobs having been successfully accomplished for a period of time? Looking at project profiles on a company website can be a great way to look at the legacy of a product, whether it applies to your hydrothermal region or your specific climate region. Cost, obviously, a little redundant there, but adherence to the substrate becomes important depending on, and this speaks, of course, to not one waterproofing system is great for every situation, depending on your substrate. Looking at new or old construction, positive or negative. We'll get into some of the materials, but some of them essentially work much better with some kinds of substrates, and some do not. So the adherence of the product to the substrate should be considered. Puncture resistance becomes very important in blindside applications. When we're doing the structural steel work over the waterproofing layer that's already been placed, the puncture resistance of a material becomes very important, because obviously if you're working with some kind of material that's easily punctured or burned when we're doing supportive excavation work or cutting of steel and rebar over these membranes, it's important that they are resistant to the types of abuse they may come up against with the work at the job site. And that, again, becomes sort of a higher liability in blindside applications where we're working on top of the waterproofing membrane. And then, of course, in those instances as well, resealability becomes very important, because we're going to have to inspect the waterproof layer before the concrete is poured. Often that will be behind the placed structural steel elements that are going to be absorbed into the concrete when it's poured. And being able to seal quickly and effectively can really speak to our labor costs, depending on how easily or how difficult it might be to reseal a certain type of error or void in a membrane. So we're going to talk about types of materials: sheet membranes, fluid applied, conventional, cementitious. Let's get into some of the materials themselves. Self-adhesive membranes consist of a polymeric waterproofing membrane or rubberized asphalt along with a high-density polyethylene carrier sheet. These are some variations in these systems, such as differences in thickness or carrier sheet, depending on the application. For example, when one of these materials is used with an asphaltic wearing course, the material is slightly thicker, and instead of a polyethylene carrier sheet, they have a heat-resistant polypropylene carrier sheet. This is for like bridge decking, where we're going to be putting a hot overlay onto the waterproofing material. That polypropylene carrier sheet is going to resist the heat of the asphalt. These systems can be applied both vertically and horizontally, and the application does include a substrate primer. And again, I would point back to that slide before that said the adherence to the substrate is important. If you're using a fluid applied good, not as important as maybe placing a peel and stick or post-applied waterproofing product where we're going to have to prime and make sure that the surface prep is correct to receive the material. So just be aware of that. Self-adhesive membranes are fully adhered. It's fully bonded to the substrate, preventing channeling of water behind the membrane. That can potentially happen if a system is loose laid. They're factory controlled. There's no reliance on the applicator of the material to provide, a specific applied thickness. They've got a factory selvage edge. There's a lot of really positive things that can be attributed to these self-adhesive membranes. A lot of redundancy built in and a lot of room for success there, which is realized differently in fluid applied applications where we have real reliance on the applicator to create thickness and continuity and make sure that the system is applied correctly. So they're also these self-adhesive membranes cold applied, so it eliminates the need for heating equipment and danger from hot materials. They're easy to apply. Once the substrate's prepared, it's usually primed and the backing's peeled off during the application, and some say it's similar to applying wallpaper. The membrane is then rolled, and any penetrations and terminations are detailed with a compatible mastic. You can see that on the footing there, those little black lines. That would be a compatible mastic to just seal the leading edge, and sometimes termination bars are used as well. So they have excellent elongation and flexibility to address movement, crack bridging, small cracks. They're compatible with a number of substrates, and it's important to ensure that the substrate is relatively smooth to ensure the full bond of the membrane. Great products. Wanted to mention thermofusible. They have all the advantages of the peel and stick membrane. However, they are not cold applied, they're hot applied. Rely heavily on the applicator to create a proper installation, but all of the positive attributes of peel and stick systems and self-adhesive membranes would apply to that as well. Not super applicator dependent on thickness, selvage edges, all of the factory controlled things that these membranes would then appear on site with. But the application itself can become a little unwieldy and certainly dangerous with an open flame. Fluid applied membranes come in two different forms, hot applied and cold applied. We'll talk about hot applied first. So hot rubber waterproofing systems consist of a rubberized asphalt compound that forms a strong, flexible, monolithic waterproofing membrane that adheres virtually to any surface, even rough, uneven surfaces. And once applied, as I mentioned, it's monolithic and free of seams. It's also, very importantly, watertight and eliminates water migration. So it offers strong protection because of the method of application, typically applied by a certified or approved waterproofing specialist, fully trained in the application using a hot system. Typical application consists of priming the surface first. The product's then applied in layers. Usually the first coat of hot liquid rubber is applied. And then usually today the fabric reinforced sheet is quickly and firmly pressed into that hot layer. And then a second coat of hot liquid rubber is then applied over the first. Because of the reinforcing fabric and really the reinforcing fabric, the elasticity of this product can be a little lower than some of the others. Because it's hot, you have to be very careful, of course. The best, of course, is to have it applied by a certified specialist. Reinforcing is added to allow a second layer to become integral with the first. And more importantly, the second layer was used to address pinholing that was seen occurring early on in the use of this type of membrane system, where they put down like 180 mils of hot rubber, and the moisture in the substrate would often turn into steam and pinhole up through the material. So in order to mitigate that, we usually do 2 lifts with a fabric in between, about 180 mils. Cold applied systems, 1 component and 2 component. They're polymer modified, water-based products, multiple applications, lots of different forms of them out there. They provide a seamless membrane. They can be applied to green concrete. Great systems. Really not a whole lot of negatives at all with cold applied systems. The one thing, again, to be aware of is that with all fluid applied systems, they're very applicator dependent on the continuity of the system, the thickness of the system, and making sure that it is a proper installation. 1 and 2 component materials typically are the 1 component materials are typically moisture cure products, some kind of STPE or silo terminated polyether that will cure in the presence of moisture. They're low VOC, easy to use in high trafficked areas. Unlike hot applied system, there isn't a lot of negative sides when you're working in a highly trafficked area around a lot of people. There's very low smell, and it can be very advantageous in some dense environments. 2 component, typically just a 2 component chemical cure for areas with low moisture, where a moisture cure product wouldn't really work that well in desert areas or something like Las Vegas. Thinking a lot of sheet good systems have an ancillary detailing membrane, which is a cold applied either 1 or 2 component system. The 2 component tends to set up very quickly and is a little more resilient than the 1 component in the immediate. And if you're looking for a quick fix to a detail, using a 2 component instead of a 1 component, it can set up a lot quicker. Blindside systems, as I mentioned, this is a form of positive side waterproofing. It's positive side waterproofing done backwards or inside out, and consists of a sheet applied membrane. Usually, not all blindside systems are sheet goods, but the majority of them are. So before going any further, let's define the blindside system again. It's a positive side system that's done backwards or on the inside of supportive excavation, where we have party walls or zero lot lines and the inability to post-apply waterproofing after placing a foundation wall. So you're essentially placing the waterproofing on the inside of the supportive excavation, usually a drainage layer, some insulation, and or protection for the membrane. One of the most important things about placing a blindside system is making sure that the manufacturer's installation instructions are followed. Very importantly, the adherence to the top of the lagging becomes a real issue. One of the things we see out in the field is the failure of blindside systems when they are literally dragged down the wall while the concrete is being poured, because the adherence to the top of the lagging wasn't correct. So if we can place a termination bar, just make sure that it's properly adhered when the weight of the concrete is poured into the forms, the material itself will not be dragged off of the substrate. Bentonite sheets, I'm not going to talk too much at length with bentonite. I don't have a ton of experience myself with Bentonite sheets, but they are very green. They're prefab panels of craft biodegradable paper, or HDPE, and nonwoven fabric, or just fabric, with a sodium bentonite, not calcium bentonite. Swells up to 15 times the dry volume. So this is a naturally occurring clay that is encapsulated into a rolled good, and then when introduced to water, of course, it will swell. It does best when it remains in areas that are completely hydrated. So it needs moisture to work. Partial hydration could be an issue, as it'll dry out and crack, and then when water is reintroduced, it can move through the flow paths until the bentonite has swollen back to its, turgid form. Soil contamination could affect the product. It's very difficult to detail. It's also a very heavy membrane, so depending on where your below grade application is going to be, if you don't have a boom truck to move it in there, sometimes can be a little unwieldy in getting into a job site. So they're heavy rolls, but however, it is a very green system. It's a great system. It works, and works best in full hydration. Spray applied systems, also not going to talk too long about these, but there is some that are out there on the market. Spray applied systems as related to below grade waterproofing typically are, field installed polymer modified asphalt sprayed onto the backside of a drainage board, essentially, and following this with fabric, and then the spray essentially that creates a monolithic waterproofing membrane. So sheet membranes consist typically, and then we're talking below grade, in two forms, usually an HDPE membrane with pressure sensitive adhesive, which is activated by the heat of hydration of the concrete being placed, and bituminous membranes that incorporate the embodiment of the membrane into the concrete once poured, containing nylon fibers. So there's a fabric on that layer that is absorbed into the concrete. Typically, in both situations, really, the adherence to the substrate itself is very important, and in order to create a situation where we don't have lateral water migration or water migrating behind the material has to be clean and ready to receive the concrete. So on a job site where we have mud or detritus or all kinds of things that are just sitting on the surface of that waterproofing membrane, when we pour the concrete, if we have mud or whatever it is, preventing the concrete from hitting the surface of the material, we're going to have voids in between the material and the substrate itself. So in either case, whether we have a chemical or a mechanical bond, both of them really need to be inspected before the concrete is poured, and certainly in a blindside application. Difficult details. Again, this speaks to our 90 to 1% principle, talks about continuity. I can't stress this enough. The two most important waterproofing principles are that, the leaks usually result from 1% of the envelope and its total exterior surface area. Meaning that, again, that balloon analogy, if we take a balloon and we put a pin to it, we have no more balloon. If we have a blindside waterproofing application that's literally unreachable, and we introduce a detail that's less than resilient, we're going to see leaking, and the waterproofing installation is then compromised and useless. And costly measures are going to have to be addressed, such as injection of many different kinds to get either into the substrate with like a methacrylate, or some kind of polymerized grout onto the positive side to actually just cover up the void that's introducing the water. But beyond stressing this, there's really no more important part of a waterproofing installation or an effective waterproofing installation than continuity. And continuity comes down to that 1% of the envelope's total exterior surface, which is our details. Making sure that we have those details in place is very important. Membrane protection. It's important to note that these protection boards are not flexible. I've seen a few situations where they're specified on an on-grade situation where they'll need to undulate or move up and down from a flat plane to accommodate some kind of parging around a column. And it's important that we're protecting the membrane, but we have to make sure that we protect it with the correct material. All waterproofing materials are going to need protection of some form, and protection boards can accommodate that. You just need to specify them in the correct place and use them in the correct manner. Prefabricated drainage layers. I'm going to talk briefly about these. Kind of the takeaway from prefabricated drainage layers is that they come in all different types of form, compressive strength, flow rate, the effect of which can be measured through ASTM 4716. What I want you to take away from this is that if you use prefabricated drainage layers, you're doing yourself a favor on your projects. They work. They were over engineered based on the Weather Bureau in North America. So the maximum rainfall, about 5 inches per hour. And the flow rate of like the smallest drainage mats will certainly accommodate what is coming out of the sky. And the most important things to remember is just make sure that we're using the correct compressive strength. The correct type of drainage mat is important. Some of them have a backer or a film to assist in backfilling situations where we don't want the membrane to drag, and we don't want the protection material to essentially create friction between the membrane and the drainage layer. And then also, of course, we want to make sure that if we're using a fluid applied membrane, we don't want to stick a drainage mat on there that is going to absorb some of that fluid applied membrane and create a less than ideal situation where the flow paths are full of waterproofing membrane. So using a backer when we're using fluid applied membranes is important. We're going to talk about crystalline waterproofing to finish this presentation up a little bit. Crystalline waterproofing materials can be used in a variety of waterproofing applications. Materials consist of cement or silica and some proprietary chemicals. They work by forming a crystalline structure in the presence of water, ultimately plugging the pores or the capillaries, the microcracks, and other voids in the concrete. One of the advantages is that the product becomes integral with the concrete. When it comes to the waterproofing of cracks, which will develop, there are different arguments about whether this works or doesn't. There's a possibility of crystalline materials activating in microcracks and sealing off that crack, but cracks of significant size will require other methods of waterproofing. There's also the potential for concrete to self-seal in some situations. So the question comes up, is the crystalline doing this, or is the concrete itself doing this? Since the concrete does crack, and it's sometimes difficult to know where these cracks are going to occur, crystalline materials may not be the most effective method in some situations. Application of crystalline materials can be done in one of three ways. The first and most popular method is where the product's mixed up and surface applied to the concrete, and it can also be added directly to the concrete and at the ready mix plants, or integral essentially. Or it can be sprinkled onto fresh concrete slab, similar to the method of application for dry shake hardeners. So essentially, what the takeaway here is for crystalline waterproofing is that it can be wonderful as a waterproofing material within a very thick slab. It protects the substrate itself, but best used as sort of a belt and suspenders approach to waterproofing as a two-part component of an effective waterproofing system. Again, having crystalline waterproofing within the mix and within the concrete is going to assist in waterproofing, but in areas where we have pipe penetrations or we have expansion joints or cracks, crystalline waterproofing is not going to be up to the task of doing that. Here you can see some of the ways that crystalline waterproofing is applied, surface applied. You can see it being troweled on and sprayed on. Again, limitations of crystalline waterproofing are vast, and it's best used as a belt and suspenders approach, or a two-part to the whole. So larger dynamic cracks aren't going to be waterproofed with crystalline. Failing water stops, areas of poor concrete consolidation, penetrations through. So flexible cementitious coatings, another type of waterproofing that's available. These products can be applied in the same applications as crystalline materials because they possess similar characteristics, and they're breathable. Therefore, they can be used on both the positive and the negative side of a wall. However, they are far superior in a number of other characteristics, along with breathability. They are polymer modified, so they can bridge cracks. They've got great elongation and flexibility of the coating, which not only allows for movement if it happens, but also provides the material with crack bridging capabilities. The product can bridge cracks typically up to about a 1/16 of an inch, and can be used in larger cracks utilizing non-woven fabrics, and a specific application procedure where the fabric is embedded into the coating on those larger dynamic cracks. So flexible cementitious coatings are a great negative side waterproofing system and will assist in your effective waterproofing. In summary, there's a number of different systems that are available. So waterproofing of a structure constitutes an essential component in long-term durability and performance in design and construction, represents a key element of any project, and as a result should command significant attention. Moisture infiltration and humidity can cause serious damage, and if water in liquid form is present, the impact can be catastrophic. So we need to encompass that with vapor proofing. There can be structural failure, or the structure can become uninhabitable. And as discussed, certain systems can make sense for specific applications and situations. For example, in a blindside application, a sheet membrane is going to be preferred over an integral crystalline waterproofing material for a number of reasons. The membrane prevents the moisture from penetrating into the concrete, where the moisture could result in freeze-thaw and corrosion problems. At the same time, the membrane provides moisture protection despite weakness in the concrete substrate that could include cracking and poor consolidation. So a number of additional waterproofing systems are available in the marketplace, including epoxies and urethanes designed for specific application. The critical issue in evaluating and specifying materials for any potential application is the realization that all systems and technologies come with strengths and limitations. So not one solution is the answer for every application. As in any project, the role of participants in the design and construction team is critical in the success of waterproofing. And when considering such technologies for long-term performance, the team approach is a must. During design, the architect needs to consult the manufacturer to ensure that correct material is being selected and is being incorporated correctly. And during construction, it is essential that the installer be fully trained in the application of the system and is able to communicate any concerns that may arise during this installation. This will lead to the assurance that the waterproofing has been installed correctly and any potential issues have been addressed. Moisture infiltration into the structure is one of the most common sources of litigation, as I mentioned earlier, and making selection and installation of the correct waterproofing system pivotal to mitigating the risk of any immediate or longer range problems, as no one solution is the answer to every situation. So thank you so much for your time. If we have anybody that would like to stick around, I'd be more than happy to answer some questions that came in. At this point, I'm going to end the presentation. I thank you all for your time and attention for joining me today, and I look forward to answering all of the questions that came in privately. And thank you so much for your support of W.R. Meadows, for joining us today for the presentation. If you have any questions, feel free to email us info@wrmeadows.com. and I'm going to leave you up here with my information. If you have further questions, please feel free to reach out to me personally. And I thank you for your time and attention today in attending Effective Waterproofing.